Good morning, student. In the last class, we discussed about vector algebra and different kind of vector addition, subtraction, vector product consisting of the dot product and the cross product, as well as the vector triple product. In this class, we are going to learn in details about some vector operators like gradient, divergence, and curve. These three are mostly use vector operator in whole of physics, and whenever you study some new topics in physics, you are always going to get through this mathematical operator. Okay, these are known as vector operator. Now for your information, operators are nothing but some mathematical entity which do certain things. For example, addition, then subtraction, then division, then multiplication. These are nothing but some mathematical operator. Similarly, we can define such operators for vectors also. Okay, gradient, divergence, and curve are this kind of operators. Okay, so before you learn about gradient, divergence, and curve, one have to introduce themselves a quantity called an operator, a mathematical operator called delta or nabla operator. Okay, delta and nabla by definition is given as del is equal to the reverse triangle, and symbol is reverse triangle. This is by definition. By definition, del is equal to I cap del by del x plus j cap del by del y plus k cap del by del z in 3D. Yeah, this is the definition of delta operator. Okay, here I cap, j cap, and k cap, these are unit vector along the direction of x, y, and z, and del by del x, this is the partial differentiation with respect to x, del by del y, partial differentiation with respect to y, and del by del z is nothing but the partial differentiation with respect to z axis. Now let me briefly remind you what is the difference of a partial differentiation and total differentiation. For example, suppose we have a function fx is equal to x square. Okay, it is a single valued function because it's the only variable here is x. So if we want the derivation differentiation for this function, we can write df by dx will be equal to twice x. Okay, so df is equal to twice x into dx. Okay, so 2x we can write is as again df is equal to df by dx into dx. Okay, so we can write it some like that also. Okay, in mathematical notation. But if fx is a function of multiple variables, say it involves x and y or z also, we cannot then the differentiation of the function can be expressed with respect to partial differentiation. Suppose fx is equal to fxy is equal to x square plus y square. Okay, so now we have to now if you are asked to find the total differentiation of the function, then df in this case, then what you have to do, you have to first partially differentiate with respect to x. Okay, df by dx into dx this way, plus next we have to differentiate with respect to y, del f by del y into dy. Okay, so this is the definition of differential if the function is a multiple variable function, and this is the definition if it is a single variable function. Then in that case it's very easy, but we have to use the notation of partial differentiation if fx is a function of both x and y. Okay, when we differentiate f with respect to x, then we have to take y is equal to constant. Okay, and when we differentiate with respect to y, we have to take x is equal to constant. Okay, this is kind of a chain rule of partial differentiation. Okay, so here in the delta operator symbol, we have to use this partial differentiation. That means when we differentiate with respect to x, we take that other two component y and z is constant, and this holds good for y and z also. Okay, so this is the definition of delta operator. Now from this definition itself, it is clear that delta is a vector operator, because you see here the x component is del by del x, y component is del by del y, and z component is del by del z. So delta is basically a vector operator. Okay, so when we want to apply the delta operator on scalar field and the vector field, there are certain rules you need to understand. For example, this is a vector, so in order to apply on a vector, then there will be two ways possible. First, we have to suppose if f, x, y and z, this is a vector field. Suppose it's a vector field. Okay, so if we want to operate this vector field with this delta operator, then we have to consider two kind of product, because in vector multiplication there involves always dot product and cross product. The same philosophy also holds good here. Okay, so if we want to operate this vector field with this operator, so we can consider two different things. The first thing is what? First thing we can consider del dot f, del dot f vector. Okay, this thing we can consider, right? Then we can consider del cross f vector, because this is also vector and this is also vector. So in order to operate this vector with this vector, therefore we have to consider the product. And this product, since these are two vectors, there can be two types. One is dot product and another is cross product. Okay, so first we have to dot this vector field with this delta operator, then we have to cross this vector field with this delta operator. Okay, and if it is f x y z is an scalar field, if f x x y z is a scalar field, then what we have to do, we have to just ordinary multiplication. This is not dot, this is not cross. Okay, this is just ordinary multiplication, del f. Okay, so this definition is possible, this definition is possible, and this definition is also possible. Okay, but we cannot have a definition like del f vector, because it doesn't mean anything. Okay, this is a vector and this is a vector. In order to operate this thing on that thing, either we have to consider dot product, we have to consider cross product. We cannot consider ordinary product between two vector quantity. Okay, so this definition is never possible. This is not possible. Not possible. Okay, so when we operate with a delta operator, either scalar field or a vector field, then we have to consider only three cases: del f, del dot f, and del cross f. Okay, and this quantity del dot f is known as the divergence of f vector field. Okay, del cross f, this is known as the curl of f. Okay, and the ordinary multiplication of delta operator with scalar quantity, this is known as gradient of f. Okay, sorry, scalar field, gradient of a scalar field. Okay, so in the next page I am going to derive del f, del cross f, and del dot f in for three-dimensional case, because if we do the three-dimensional, you can easily generalize to one or two dimension. Okay, so let me first compute what is del f, del cross f, and del dot f. Okay, so first we consider the gradient of a scalar field, because if we take a gradient, it has to be a scalar field. Okay, so suppose we have a scalar field f x y z. It can be anything, say temperature field, or say mass distribution field, these are all scalar field because temperature can never have a direction, so it can be scalar field. Okay, so say this we can say twice x square plus 4y plus z. Okay? This is a scalar field. That means if we put the value of x, y, z at this point, if it is a temperature, then we can obtain the value of temperature at that particular point. Okay, so this is a scalar field. Now the gradient of this field can be mathematically written as del f. Okay, then delta operator is del by del x plus j by del y plus k del by del z. Okay, then what we have to write, f x y. Okay, so first I am just going to write the formal definition, then we can do some problems always. So this will be I cap del by del x f x y z plus j cap del by del y f x y z plus k cap del by del z f x y z. Okay. Okay, so this is the definition of a gradient of a field. Just you have to put the value of f x y z here in order to compute the gradient of this scalar field. Okay, now we can see the gradient of a scalar field is always a vector quantity because this is a vector, because this vector's x component is del by del f by del x, this vector y component is del f by del y, and z component is del f by del z. So gradient of a scalar field is always a vector quantity. You have to remember that it's a vector quantity. Gradient of a scalar field is a vector quantity. That thing you have to remember. In the next part of the class, I am going to discuss the physical meaning of a gradient of a scalar field. For the time being, it's just confined with the definition also only. The next were divergence of a field. Divergence of a vector field, because we are considering the dot product, so it has to be a vector. Okay, and it's written as del cross f vector. So what we can write, I here, and here you see it's a vector quantity. F is a vector quantity, so we can write f is equal to, for if we take this example, then it will be twice x square into I cap plus 4y into j cap plus z into k cap. Okay, so it's a vector quantity. So del by del x plus j into del by del y plus k cap into del by del z. Okay, and we can write f as fx into I cap. This thing we can write plus fy into j cap plus fz into k cap. Since it is a vector, we can resolve it into components and write like that. Okay, now we have to dot this quantity with the delta operator to get the divergence of this quantity. Divergence also has physical meaning. I am going to discuss it in the next part of the video. What is the physical meaning of a divergence of a vector field? So right now just confine with the definition, right? Dot, we can write now fx into I cap plus fy into j cap plus fz into k cap. Okay, so this is the definition. Okay, now you see I dot I will give you 1, I dot j 0, I dot k 0. So when you consider dot product, we have to only consider the similar terms. Okay, similarly for j this term will be there, and for k vector only this term will be there. So when we do the dot product, then it will become del fx by del x I dot I we know it's equal to 1. Okay, plus del fy by del y plus del fz by del z. Okay, so you can see del dot f, is this a vector quantity or scalar quantity? This is a scalar quantity because I dot I, it will give us 1, so it doesn't have any direction like I cap, j cap, z cap, it doesn't have. So divergence of a vector field, it will be always a scalar quantity. Okay, so this is the second mathematical operator which we used to do in vector. Now the last operator is curl of a vector field, and mind you, these all operators have very deep physical meaning. So I am going to discuss in the next class what are those physical meaning. For the time being, the definition is sufficient. Okay, now the next will be the curl of a vector field. The curl of a vector field. Okay, how it is defined? It's defined as, if f is a vector field, then how it's defined is defined as del cross f. Okay, this is known as the curl of a vector field. As always, we can do the determinant notation in order to write this cross product. So I cap, you can write j cap into k cap. Here, what is the ith component? Delta operator, del by del x, jth component, del by del y, kth component, del by del z. Okay, and here ith component fx, this is fy, and this is fz. Okay, so we can write I, if we take the first row, I will be equal to del fz divided by del y minus del fy over del z. Okay, this is ith component, plus z component will be how much? Del fx by del z minus del fz by del x. This is the z component, plus what is the kth component? If we do the kth component, del fy by del x minus del fx by del y. Okay, this is the kth component. So this is the definition of curl of a vector field. We can easily compute if we know the value of fx, fy and fz. Okay, so to find the curl of a vector field, we just have to cross product the del operator with f. Okay, and one thing I forgot to tell you, this operator is known as the differential operator. You may have understand why it's known as the differential operator, because it always involves the differentiation of a particular quantity with respect to x and y and z. Therefore, in physics, the del operator is known as the differential operator. And we have defined three operations with this differential operator. One is curl, one is gradient, and another is divergence. Just like plus, minus, division, and multiplication we define for ordinary scalar quantity. Okay, so thank you. And in the next class, I'll briefly explain you what are the physical meaning of gradient, divergence, and curl of a vector or curl of a vector field. Okay, thank you.